Hello and welcome again to Physics Galaxy. So last time we saw that electric field can be written as the negative gradient of a scalar function V, which we called electric potential. So V was our electric potential. Okay, so this was the differential form. So this was our differential form. Then we also introduced the integral form of the same equation. So integral form. So which was that the change in the potential is equals to the line integral of electric field, that's integral E dot dl with a minus sign. Okay, so keep one thing to keep in mind is that here we have this upright triangle. So this upright triangle always denotes change. Okay, so mostly it denotes change, but in this equation we have the upside down triangle, which is the symbol of gradient. Okay, gradient. So never get confused. So this was the our definition. We can also say this was the definition of our potential. So in other words, if we have 2 points, suppose we have point A and point B, and we choose some path. Suppose this was the path connecting A and B, then we can write that the change in the potential, that is VB minus VA, equals to minus integral A to B E dot dl. So from this we can get the change in the electric potential function. Okay, so not only change, if we choose some reference, suppose we choose some reference point, suppose we take as R0. Okay, so then we can assume that the potential at the reference point are not equals to 0. So in that case, what we'll get, potential at any point r can be written as the negative of the integral infinity to r E dot dl. So we can get the potential at any point in our field. Okay, in our space basically, by choosing the appropriate reference point. Okay, so we always have to choose an appropriate reference point. So by appropriate, I mean that it changes. So usually if we have finite charge distribution, so if we have finite charge distributions, that means we can have, suppose, a potato shaped charge distribution, or suppose a little cylindrical charge distribution, or a surface charge distribution. So it can have only line charge distribution, volume charge distribution, or surface charge distribution, but it should be finite. Okay, then what we can choose infinity as our reference point. So infinity can be chosen as our reference point. So if we have the finite charge distribution, so only in this case we can choose reference as our reference point, infinity as our reference point. And for infinity we know that all fields vanish. So all electric fields, potentials, everything vanishes at infinity, but only for finite charge distributions. If we have infinite charge distribution, then this condition doesn't hold. Okay, so potential at r equals to minus integral infinity to r E dot dl. So this is the definition of the electric potential function, okay, in electrostatics. Now, as I said, if I have finite charge distribution, so finite charge distribution and finite charge distribution, and if we put one more condition, that charges are either positive or negative. Okay, only one charge, only one charge. That means it can be only positive charge or it can be negative charged. Okay, either positive only or negative only. Then in this case, we can write that the electric field to a good approximation varies as 1 over the length square. Okay, so when these are the condition, electric field to a good approximation vary does vary as 1 over length square. So what we can see from here is that if electric field varies as 1 over length square and there is multiplied by the length itself, so it's L. So 1L and 1L will get cancelled out. So in this case, the potential will always vary as 1 over L. Okay. So if we have suppose some question regarding like suppose you have some cylindrical charge distribution and the questioner asks what is form of potential at some sufficiently large distance, so you can guess that potential will vary as 1 over the distance, suppose r. Okay, and the electric field will vary as 1 over r square. It doesn't depend upon the shape. It can be suppose any kind of general shape. So this will always be true that potential to a good approximation will vary as 1 over r, and electric field to a good approximation will vary as 1 over r square when these are the conditions: finite charge distribution and only one type of charge, either positive or negative. So by this condition I mean it should not be like this, like suppose if you have a cylindrical charge distribution, there is positive on one side and negative on one side, so this does not apply for this case. Okay, now what else can we get from this equation? E equals to minus gradient of scalar function that we call potential. Okay, so one thing is that we can multiply by charge on both sides, so we can multiply charge on both sides. Okay, so we can multiply charge on both sides and see what else we can find. Now charge times the electric field is simply Coulomb's law. Okay, that is the force F equals to Q times electric field, which equals to minus gradient of Q can be put inside, so Q times V. Okay, now Q times V is a different quantity that we call electric potential energy. Electric potential energy. Electric potential energy. So we can write F equals to minus gradient of U, where U is the electric potential energy. Okay, so this is the differential form. Differential form. Okay, now if we want to find the integral form of the same equation, integral form, so we can write change in the electric potential energy equals to minus of the line integral of force, that is integral of F dot dl. So like we did in the previous case. Okay, but this integral of F dot dl is the work done. Okay, W, so we can write W equals to minus the change in electric potential energy. Okay, so this is some of the results that we got from this equation. E equals to negative gradient of potential. So what else can we get from the same equation? So E equals to minus gradient of potential. So one thing is that we can use Gauss's law, because in that equation we have electric field. Okay, so we can use Gauss's law that says the divergence of E equals to rho over epsilon naught. So we can put this E into this equation here. So we'll get divergence of, so in place of E we'll write negative gradient of V, which equals to rho over epsilon naught. Now minus can be taken out and it can be put into this side, so we'll get divergence of gradient of V equals to minus rho over epsilon naught. Now this thing, divergence of a gradient, is called the Laplacian. So del square, it becomes del square of V equals to minus rho over epsilon, so which is a famous Poisson's equation. Okay, so del square V equals to minus rho over epsilon. So in the from this equation, if we know the charge distribution, okay, we can directly find the electric potential. And from electric potential we can take the gradient of V and we can get electric field. Okay, so this is the algorithm basically. If you know rho, you can find V by using Poisson's equation, that is del square V equals to minus rho over epsilon. And if you know V, you can take the gradient of V, find the electric field. Okay, so this is one way to find the electric field.